Now we're talking about this particular unit. We're focusing on public transportation. Again, you'll see a lot of this, there are lots of similarities. How do you monitor how the transit system is working? How do you take corrective actions when you have buses behind schedule or things of that nature? How do you get information out to travelers to make better decisions? So, there's many similarities here to the highway mode we've looked at earlier. I do ask you to look at some of the discussion questions in the forum. Some of the things I think will be interesting. How will things change moving into the future in terms of trip planning, for example? You think we will? Most transit systems today have their own trip planners. So is that going to continue? Do you think? There's discussion of G-force monitoring, where you can essentially monitor driver behavior on buses. Just for what it's worth, that's something that you can easily do today with a cell phone. In fact, we've done similar work for monitoring pavement roughness using the accelerometers on a cell phone. You can easily do this to monitor driver performance as well. So there are some things that you'll read about that even 10 years, 5 years ago were very difficult to do with a large-scale system. Today you can do simply with the cell phone network. Then we'll also talk about electronic tolling and pricing. And you'll see they talk both about the technology and they also talk about the strategy. We got into the strategy discussions back in the forum for last unit. But it's interesting to see here that as we can collect user fees electronically, what does that allow us to do in terms of funding these systems and managing these systems? And you'll see discussions of things like managed lanes, etc. So another good unit, module. Please do take good care in reading that and participate in the discussion. So now let's move and talk about the case study. And this case study is focusing on, let's see here, and I apologize, there's a lot of early slides we don't need to worry about here. Now I'm going to move past them pretty quickly. This is on adaptive traffic signal systems. The slides I passed were slides that we've already discussed these sorts of things, quite frankly. So for adaptive signal systems, we did talk a bit already about how signals work. We looked at the cabinet from Utah, and here's another example of a simple cabinet. This is from 2002. You see in this image. Things haven't changed dramatically since 2002 in terms of the componentry for a cabinet. But basically, again, we're getting in detector data. We have a controller, which is this unit right here, that is the brains of the operation, and we are assigning right-of-way based on the control algorithm. One interesting note, what you see here for presence detectors are actually video presence detectors. So as opposed to using loop detectors here, they are using something like, for example, an autoscope, where you basically look for changes in pixel intensity in these zones as the presence of a vehicle. Just quickly, there are simple, the traditional way has been what's called a fixed timing plan, where you say, okay, every cycle we're going to assign so much time to different movements at the intersection. This works well for very predictable traffic flows. We've moved in many cases to what are called actuated signals, where you have a basic timing plan, but you can extend the length of phases based on vehicles actuating detectors. So in other words, if you have a green phase and a vehicle comes in within some amount of time and actuates that detector, then that phase will continue to allow that vehicle to pass through. So the idea is to try to, to better manage a little bit of unpredictable traffic flows. So you'll see a lot of actuated signals in use, and also there's still plenty of places where you have fixed time signals. In terms of signal control basics, and again, you all are familiar with traffic signal control, whether through classes or through being a driver, quite frankly. There are things that don't work well about signals. I mean, some of you might have been on bicycles at an intersection, and you don't actuate the controller, and you have to sit and you don't get the green phase. There are times when I don't know if you've noticed, when you have an emergency vehicle come through, that gets a preemption, but then really affects the coordination of signals for a quarter for a long period of time. So this is another issue here in terms of signal management. again, just to kind of fill in the gaps here. We talked about time-based, where you had basically a control plan based on time. We had traffic responsive, where you're trying to manage more based on actuation, responses to traffic flow. Traffic adaptive is what we're going to talk about in this particular module. And in traffic adaptive, what we're really trying to do here is it's the highest level of coordination, and basically there are physical connections between your intersections and the algorithms where you're looking at demand and you're modifying your signal timing plan on a real-time basis. So in other words, you're constantly looking at what the actual demand is and you're modifying your plan to meet that demand. So if you're in a very predictable corridor, traffic adaptive does nothing for you, right? Because it's predictable. You're not going to be adapting because there's nothing to adapt to. If you're in a corridor where you have lots of fluctuations, this can be very, very useful. Again, what does traffic adaptive signal control need? It needs a higher level of input data. What are the demands out there? It needs a better controller to do the search and the optimization. But it's certainly something that we can do today with the technology that we have. We're not doing so well overall in terms of traffic control, traffic signal performance in the country. Again, why is this so low? Many cases because we haven't put the time or the effort into traffic signal timing. Some cases where you're running very old equipment. I mean, I know there are some places in cities where we're using electromechanical systems that are literally from the 50s or 60s. Again, why do we get away with that in cities? Because typically they are running fixed time because you have very predictable, highly congested areas. You really can't play around with timing plans to favor one corridor or another. Every direction has high demand. But again, the message here is that there's a lot of work to be done, and there's been a lot of attention paid on using ITS. And again, the idea of better detectors, better monitoring, higher level of computing performance to better adapt signals to the current demands. We're going to talk about that in this case study. For example, we're involved right now at UVA in what's called the MITS project, the Multimodal Intelligent Traffic Signal Systems project, which is a connected vehicle-driven adaptive signal control system that's being prototyped in at least 3 states now, in California, Arizona, and Utah. Again, the same idea holds that we're talking about here in adaptive signal control. Taking a higher level knowledge of traffic flows, better ability to optimize signal systems, and then having a more adaptive system. Again, this is a pretty straightforward example from this slide deck they give with a case study. For a programmable adaptive thermostat, you're looking at how long it takes to get up to a set point, how quickly you fall away from a set point. It's much more simple than just trying to get to a number and stay there. So again, the idea here, and I'm not sure I really love this example because I think a digital programmable adaptive thermostat is really pretty simplistic compared to doing this from a traffic signal control system where you have multiple intersections. This gives you, unfortunately, a pretty old video from the Los Angeles traffic control system. This is what I'm not going to play it right now in the interest of time, but you can go online and Google this. It's a Vimeo video, Vimeo. It's not on YouTube, to my knowledge. You see, actually, Vimeo is right here. But you can find this, play the video, and again, you'll see that this system was really started back in 1984, which I know is well before when many of you were born, for the Olympic Games when they were in Los Angeles. But again, LA is considered a leader in trying to more adaptively manage their signal control system. So moving on from the example from Los Angeles, again, this slide we're talking about, adaptive signal control technology is effective when you have varying levels of demand that you want to be able to adapt to quickly without doing a retiming effort. How much does it cost? The cost is at least $50,000 per intersection above the current infrastructure. Where does that cost come in? Primarily comes in from the higher level of detectorization. also from the software complexity and complexity of personnel to set this up. Now, the issue is this cost should be going down as we get to connected vehicles because we're going to have a higher level of resolution of data that's not coming from sensors, it's coming from the vehicles themselves. So we really think that this is something that's going to be very cost effective in the near future. And in fact, even without that, if you think about $50,000 per intersection, that's a drop in the bucket compared to what it costs for construction of lane miles. So again, this can be a very useful system. So again, what does an adaptive system do? What it does is comparing the demand, say from a certain time period to another time period, and you try to figure out what would work well. Does what works well at 5:30 also work well at 3:30? Perhaps we have a traffic pattern that matches that particular time. Maybe it's a Friday, people are leaving early. Maybe there's a special event. Who knows? But in many cases, you're trying to find patterns that match pre-timed patterns in your system that you can adapt, you can quickly modify to, regardless of the time of day. So again, the purpose of this case is not to get you to a really high level of knowledge of adaptive signal control systems, but rather to help you work through some of these issues at a higher level. Also, it's important to note, as you saw in last unit's application description project, the SCAT system coming from Australia is an example, and one of the oldest examples of a good adaptive signal control system. So you've seen that already now in this class. How does this benefit us? Number one, it can reduce congestion, reduce fuel consumption. It can basically keep us from having to do so much work on traffic timing. The current state of the practice is you need to go out there every year, 2 years, and retime your signal system, which involves a lot of counts, a lot of optimization with something like Synchro. If we can have this automatically doing that on an ongoing basis, it's more effective and more cost effective. What are the challenges here? It is more complex, which is difficult sometimes for DOTs to manage and having personnel who are ready to handle this. Sometimes your current traffic control system, your controllers, your detectors, are not able to handle the needs for an adaptive control system. Again, it's new. Anything that's new is difficult sometimes. This second to last bullet is important. Arterial volumes might not fluctuate enough to warrant ASCT. It might not be the best choice for all locations. I can tell you one of the leaders in this area used to always say that he will take a well-timed fixed time corridor over an adaptive system any day, and that is because his thought was if you have a corridor that is predictable, that's pretty the same patterns day to day, and you put a lot of effort into developing a good timing plan, that will always outperform something generated on the fly, so to speak, with an adaptive system. So again, the point is that there's many corridors that don't fit that description and need this level of adaptation. So the next slide here is really getting to and actually I've lost some of the notes here, is more for the case study itself. What I would say here is that think about this with respect to the systems engineering process. How do you put this together in a systematic way? How do you look at the needs first? How do you look at the interfaces, etc.? Again, a goal-centered approach, starting with a high-level goal, moving down to technical tactics. So what you have here for this case study is you're playing the role of a junior traffic engineer in a city known as Hamilton, where you have traffic problems on the main arterial, and you have proposed an adaptive signal control system at 15 of the intersections along the main arterial, and that you're playing the role where this is going on, and you're in this particular scenario. So you've got 4 tasks. Again, what the recommendation is, it's been about 30 minutes per task. looking at your role and responsibility, looking at the patterns themselves in existing signal architecture, looking at operational strategies you can use, and finally comparing and contrasting adaptive and non-adaptive technology systems. So that's a quick run through the case. Again, you're going to be doing by yourself. Basically what you're doing in this scenario is you're reading the material you're given, and you're just stepping back and thinking about it and responding to it. So this is a little different. You're not going to be doing any data analysis like you did for the last case. Okay, so that is your introductory video for this unit. Again, please do get involved in the discussion early and often. And if you have questions or concerns, please let me know. All right, thank you very much. Bye.